In this video, we're going to look at another type of hypothesis test called a goodness of fit test. So definition. A goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So in other words, there's supposed to be some specific distribution that's being followed, and we're going to check whether our data confirms that that specific distribution is being followed or not. And so again, we call this a goodness of fit test. So as a quick example, suppose that you wanted to check whether you have a fair die or not. In other words, if you have a fair die, then when you roll that die, it should land on each outcome, 1, 2, 3, 4, 5, or 6, with equal frequency. In other words, you should get a 1, 1/6 of the time, a 2, 1/6 of the time, and so on. So one way to determine whether that die is actually fair or not is by rolling the die a large number of times and seeing if the results that you obtain are approximately 1/6 of the time you get a 1 and 1/6 of the time you get a 2, and so on. If you do, then that would confirm that the die is a fair die. If you do not get that result, then that might be statistically significant enough to say that you, in fact, do not have a fair die. Well, that's the same sort of idea with the goodness of fit test. We're going to check our data and see if our data confirms that the specific distribution is being followed or suggests that maybe this distribution is not being followed. Now, if the correct conditions are satisfied, a goodness of fit test will be based on a chi-square distribution. So we need to define a chi-square distribution. So we have the characteristics of a chi-square distribution. First of all, it is not symmetric. Second, its shape depends on the degrees of freedom, just like student's t-distribution. Third, as the number of degrees of freedom increases, it becomes more symmetric. And fourth, the values of chi-square, incidentally, that is this symbol right here. Chi looks a lot like an X, and then we have squared, so this is chi-squared, are non-negative. That is, the values of chi-square are greater than or equal to 0. So here we have some examples of chi-square distributions. So first of all, this blue curve is representing a chi-square distribution that has 2 degrees of freedom. Then we have the pink curve here, which has 5 degrees of freedom. We have the orange curve, which has 10 degrees of freedom. The green curve, which has 15 degrees of freedom. And last but not least, the purple curve here, which has 30 degrees of freedom. So as a general rule, a chi-square distribution is usually going to have a shape something like this. It's usually going to be skewed right. But again, as the degrees of freedom increase, this becomes more and more symmetric. And so again, we're going to use the specific chi-square distribution depending on what the degrees of freedom are for our situation. So we'll talk more about this chi-square distribution as we get into our hypothesis tests. But again, this chi-square distribution is going to generally be a skewed right distribution as opposed to symmetric. We do not have negative values when we have a chi-square distribution. They will always be positive values. So like when we look up critical values or when we find test statistics, they'll always be positive, never negative. Otherwise, the way our hypothesis test is going to work is going to be pretty similar to the hypothesis tests that we've seen previously. Another concept that we need to discuss in order to be able to do a goodness of fit test is the concept of expected counts. So suppose there are n independent trials of an experiment with k greater than or equal to 3 mutually exclusive possible outcomes. Let P sub 1 represent the probability of observing the first outcome, and E sub 1 represent the expected count of the first outcome. P sub 2 represent the probability of observing the second outcome, and E sub 2 represent the expected count of the second outcome, and so on. The expected counts for each possible outcome are given by E sub I equals mu sub I, which equals n times p sub I for I equals 1, 2, and so on up to k. So in other words, the expected count is going to equal the mean, just like when we had a binomial distribution, and that is going to equal the number of repetitions of the experiment times the probability of the particular outcome. The difference between this and a binomial distribution is that in a binomial distribution, we only had 2 possible outcomes. But here we could have several possible outcomes. Again, like rolling a die, we have 6 possible outcomes. So if we rolled a die, say 600 times, we would expect to get 100 ones. And so that 100 would come from 600, the number of repetitions of the experiment, times 1/6, the probability of rolling a 1. 600 times 1/6 would be 100. That would be the expected count. So notation-wise, P sub 1 would represent the probability of rolling a 1, and E sub 1 would be the expected number of ones if we rolled the die n times. P sub 2 would represent the probability of rolling a 2. E sub 2 would represent the expected number of 2s that we would get if we rolled the die n times, and so on. Now, rolling a die, each of the outcomes 1 through 6 has an equally likely chance, so all of those probabilities would be the same. But if we were rolling, say, 2 die, then we would not have the same probability of rolling a 7 that we would have for, say, rolling a 6. And so we would have different expected values because the probabilities would be different. And we'll see this as we look at some examples. So we have an example. Determine the expected count for each outcome. So here we have a scenario where P sub I is equal to 0.15, 0.3, 0.35, and 0.20. In other words, the probability of the first outcome is 0.15, the probability of the second outcome is 0.3, the probability of the third outcome is 0.35, and the probability of the fourth outcome is 0.20. So this is a probability distribution, and so we are pretending here that this is the distribution that our scenario is supposed to be following. So again, this 0.15, that would be P sub 1, the 0.3, that's P sub 2, the 0.35 is P sub 3, and the 0.20 is P sub 4. So we want to find the expected counts. In other words, we want to find E sub 1, E sub 2, E sub 3, and E sub 4. Well, since n is 700, that means we're going to be repeating the experiment 700 times. So to calculate this, we're just going to take 700, that's n, times 0.15, and that equals 105. So if we repeat this experiment 700 times, we would expect the first outcome 105 times. In the same way, if I take 700 times 0.3, that equals 210. 700 times 0.35, that equals 245. And 700 times 0.20, that is equal to 140. So the expected count for the second outcome is 210. The expected count for the third outcome is 245, and the expected count for the fourth outcome is 140. So this is E sub 1, E sub 2, E sub 3, and E sub 4 as far as our notation goes. So again, what we would then do is we would compare data to what's expected to see if this confirms that our data is following what's expected, or is our data different from what's expected. So the test statistic for goodness of fit tests. Let O sub I represent the observed counts of category I, E sub I represent the expected counts for category I, K represent the number of categories, and N represent the number of independent trials of an experiment. Then chi-square equals the sum of O sub I minus E sub I squared divided by E sub I, where I equals 1, 2, and so on up to k, approximately follows the chi-square distribution with k minus 1 degrees of freedom, provided that 1, all expected frequencies are greater than or equal to 1, that is, all E sub I is greater than or equal to 1, and 2, no more than 20% of the expected frequencies are less than 5. Note, E sub I is equal to N times P sub I for I equals 1, 2, and so on up to K. So O stands for observed and E stands for expected. So we're going to compare what we observe in the data or in the experiment to what is expected based on the probability distribution that's supposed to be being followed. So we're going to take the observed value minus the expected value for each category, square that, divided by the expected value of the category. So again, we're going to do that for each category, and we're going to add those up, and that gives us this chi-square value. And again, that chi-square value follows a chi-square distribution with k minus 1 degrees of freedom. Now again, k is the number of categories, not n, not the number of repetitions of the experiment. So for example, earlier I mentioned that if we were to roll a die, say 600 times, that would be n. n would equal 600. But the number of outcomes, k, would equal 6, because when we roll a die, there are 6 outcomes. 1, 2, 3, 4, 5, or 6. So the degrees of freedom would be 6 minus 1, or 5, not 600 minus 1, not 599. So that's different from the degrees of freedom that we've seen previously. So again, this is going to follow a chi-square distribution with k minus 1 degrees of freedom, as long as we have a large enough sample size n so that all of the expected frequencies are greater than or equal to 1. That's the deal with that. We have to have a sample size n, or a number of repetitions of the experiment n, large enough that all of the expected frequencies are greater than or equal to 1. And also, no more than 20% of the expected frequencies can be less than 5. So we'd rather have all of the expected frequencies be larger than 5, but we'll accept some of them being smaller than 5, but no more than 20% of the expected frequencies can be less than 5. I'm going to close this video out with one final example using the chi-square distribution. So example, consider a chi-square distribution with 10 degrees of freedom. We want to find the critical value chi-square sub 0.05, and we want to find the area under the curve to the right of chi-square equals 22.346. So if we have a chi-square distribution with 10 degrees of freedom, that chi-square distribution is going to look something like this. Again, this is a chi-square distribution. 0 would be over here. And if we want to find a critical value chi-square sub 0.05, that 0.05 is alpha. That would be this area over here in the right tail. And that area right there would be 0.05. And we want to figure out what is this value here that has that area of 0.05 to the right. So this works a lot like when we were using the normal distribution and a lot like when we're using the t distribution. We just have a chi-square distribution. So how are we going to go about figuring out what that critical value is? Well, we have a table in the back of the book that we can use for this, and we have a chi-square calculator in StatCrunch that we can use for this. So if I bring in the chi-square distribution table from the back of the book, this is table 8 from the appendix of our textbook, and this is a chi-square distribution. So this chi-square distribution works a lot like the t-distribution table worked that we've used previously. Along the top here, we have areas, and these are areas in the right tail. In other words, these are areas to the right of the critical value. And so we have different columns that represent different areas. And then in the far left column, we have the degrees of freedom. And so this will work for the specific chi-square distribution that we have. So in our case, we have an area in the right tail of 0.05. So that is what this column is for. And we have 10 degrees of freedom. That is what this row is for. So if I go across this row until I get to the column for the area of 0.05, then I see this value 18.307. So that is this critical value. It is 18.307. So if the area in the right tail of a chi-square distribution with 10 degrees of freedom is 0.05, then that critical value right there is 18.307. Now our TI calculator does not have a function that's going to allow us to find this critical value. But in StatCrunch, we do have a chi-square calculator where we can find this value. So if you prefer technology, we can use StatCrunch for this purpose. So if I go into StatCrunch, I'm going to go to Stat and Calculators. This is the same place where we went previously for the normal calculator, for the T calculator, for the binomial calculator, and so on. Well, this time we're going to use the chi-square calculator. So when I select that, I get this window, which has a chi-square distribution. So the first thing that I'm going to do is I'm going to enter the degrees of freedom, which in our case is 10, so we already have that degrees of freedom. And again, in this case, I want the area in the right tail to be 0.05, and I want to figure out what the critical value is for that. So since I'm dealing with the right tail, I'm going to change this to be greater than. Again, just like we did when we were using the normal calculator and the T calculator. And I want the area to be 0.05, so I'm going to enter 0.05 out here in this outer box. When I say compute, StatCrunch returns the critical value, 18.307, which agrees with the value that we found by hand. So again, I can use this chi-square calculator in StatCrunch to find the critical value, and it works very similarly to the way that the normal and T calculators worked. Now let's look back at problem B. We want to find the area under the curve to the right of chi-square equals 22.346. So if I draw another chi-square distribution, here's 0, here's our chi-square distribution, and this is a chi-square distribution still with 10 degrees of freedom, and we want the area to the right of 22.346. So 22.346 would be here. We're looking for this area. That's what we're trying to find. Well, if I want to use my table from the back of the book, I can't really find that area precisely from the back of the book. The best I can do is this. I can go to the 10 degrees of freedom, and I can look for, in that row, the value 22.346. So if I go across the row for 10 degrees of freedom, I'm looking for 22.346, and I don't find it. I find the value 20.483, and I find the value 23.209. So 22.346 would be in between these values. Now, 20.483 has an area of 0.025 to the right, and 23.209 has an area of 0.01 to the right. Now, since 22.356 falls in between these two values, that means that the area to its right would be somewhere between this 0.01 and this 0.025. So with my table, the best I can say is that the area is somewhere between 0.01 and 0.025. So this area right here with the table, I can't find precisely, but I know that it's going to be something between 0.01 and 0.025. So that's the best I can do with the chi-square table. Now, if on the other hand I want to use my calculator, I can use my calculator for this. So I can go to distributions. This is the same place where we went when we were working with normal distributions and t-distributions. And if you look on the calculator, we have a chi-square PDF and chi-square CDF command. So on my calculator, I'm going to use option 8, the chi-square CDF command. Now let me talk about that just a second before I do it. So the chi-square CDF command is going to work like the normal CDF command and the tCDF commands worked on our calculator. So for the chi-square CDF command, I'm going to start by finding that command, and then I'm going to have to put in a left bound, I'm going to have to put in a right bound, and then I'm going to put in the degrees of freedom. So very, very much like the tCDF command that we've used previously. So if I bring back in my calculator and I select the chi-square CDF command, my lower bound in this case is the 22.346, so I'm going to type that in, 22.346. I do not really have an upper bound, so I'm going to use a large positive number, so I use 10 to the 99. I'm going to enter in my degrees of freedom, in this case 10, and I'm going to paste. Now again, if you have an older calculator, you won't get that window. You'll have to type this in directly, like is shown here. When I hit enter, I get 0.0134. So 0.0134, that is this area to the right of 22.346. And notice that that is between 0.01 and 0.025 as the table indicated. So 0.0134 is the area to the right of 22.346. Now we could also use our chi-square calculator in StatCrunch to figure out this value. So in StatCrunch, if I'm looking here at our chi-square calculator again, in this case I already have the degrees of freedom entered, and I want the area to the right of 22.346. Because I want the area to the right, I'm going to choose greater than right here, which we already have selected. And so I'm going to just type in this box here, 22.346. And when I say compute, StatCrunch gives me the area in this outer box. So I get 0.0134, which is the same value that our chi-square CDF command gave us on the calculator. So again, that area in the right tail to the right of 22.346 is 0.0134. Now, I'm showing you this example because this is how we're going to find critical values when we're using the chi-square distribution in a hypothesis test. And this is how we're going to find p-values when we're using chi-square in a hypothesis test. And so we're going to see that in the next video where we're going to conduct a hypothesis test for goodness of fit.